Hello students, welcome to Wallah. My name is Venkatrao. Welcome to lecture series on theory of computation. Today is our lecture number 15 in our subject theory of computation. Right. So our topic for today's session is undecidability. Before going to start this, please clarify me about audio, video, any issues in the audio video quality. Right. If it is everything fine, I can continue. So in our previous session, we discussed about Turing machines. So before going to start this session, undecidability. Is it clear? My audio, video, everything is clear? Students, please inform me so that I can continue my session. If you are facing any difficulty, please inform me. Good evening to all of you. Right. Thank you. So everybody is saying audio and video is clear. I'm continuing. Before going to start this session undecidability, let me give some recap on previous session, what we studied in the previous class. So our previous topics are Turing machine. In our last class, we studied about Turing machine. Turing machine. So what is a Turing machine? Turing machine is nothing but mathematical model for a computer. So in order to study the capability of a computer, what a computer can do, what a computer cannot do, the concept of Turing machine was introduced by Alan Turing. So based on this concept of Turing machine, whatever the problems which are not solvable by Turing machines, those are also not solvable by computers. So what are the problems solvable by halting Turing machines? For them, we can construct algorithm. Algorithm can be constructed so that we can write a program. So this is what the actual scenario. So whenever you say Turing machine is simply a mathematical model used generally to study about what type of problems are decidable, what type of problems are undecidable. Today's topic is based on actually our last class topic, that is Turing machine. So the main application of Turing machine are for what kind of problems we can construct algorithm, for what kind of problems algorithms cannot be constructed. That is our main aim. And the next thing is, if a problem is solvable, then P class and P class, this classification also done. Based on that, we studied what is exactly Turing machine, its diagram, and then formal definition of the Turing machine. So Turing machine even looks like finite automata. It is looking like as finite automata. If anybody missed this last class, just watch that recording. The Turing machine concept was very wonderful one. So we designed Turing machine for one of the important language as well. Right. So block diagram of the Turing machine. Turing machine, even though looking like a finite automata, but it is having powerful capabilities. What are the powerful capabilities of the Turing machine? Read-write capability, turnaround capability, infinite length tape. So by using this read-write capability and turnaround capability, in yesterday's class, we designed a Turing machine for the language, even though it is having memory comparison, even though it is required comparison, even the memory required without any problem, because we don't have a stack here till now. So even though we don't have a stack, we handle the Turing machine. Right. So in the last class, we have studied the formal definition of Turing machine. Formal definition of Turing machine, and then we constructed the Turing machine for the language. a power n, b power m, n greater than or equal to 1. We construct Turing machine for this language as well in the last class. And then we studied there are three types of Turing machine. Turing machine as a recognizer, language recognizer, and then Turing machine as a output generator, Turing machine as a enumerator Turing machine. Like this, these are the three types of Turing machine we have. For all these three types, we have to construct Turing machines. In that, in the last class, we started constructing Turing machine for language recognizer. For especially for gate examination point of view, recognizer is a more important. Does not mean that we don't get questions from remaining. We'll get questions anyhow, but the main important thing is recognizer part of the Turing machine, right? So now in today's session, so we studied the types of Turing machine as well in the last class. Types of Turing machine. So these are the topics we discussed in the last class. So on today we'll extend this discussion. So compared to the previous automata, finite automata and push down automata, what is the property Turing machine having is the language of Turing machine. If you observe the language of Turing machine, let me write here. If you observe, it will be categorized into two categories again. Like in push down automata, here we have recursive enumerable languages RELs, recursive languages REC. Recursive enumerable languages and recursive languages. We got a classification differently like this. Let us see what is the reason, for what reason this classification has come. So for that we need to move to the study of the Turing machine nature. So the Turing machine, whatever we are studying here, will show two behaviors. So whenever you say Turing machine, it takes the input. Now some Turing machines, for your input, for whatever the input it is reading, Turing machine, the property of the Turing machine is it will not halt always. Halt means stops. For some inputs it will halt, for some inputs it will not halt. So based on this, we have some halting Turing machine, we have some may or may not halting Turing machines. Like this, we can categorize the Turing machines into two categories. So we can say this is the halting Turing machine, and this is may or may not halting machine. Sometimes may halt, sometimes may fall into loop. Like this, two different natures are there based on its halting, non-halting property. How we made the classification of CFLs, DCFLs? Generally, the classification of CFLs and DCFLs is made because of different powers of this. The expressive power of DPDA, expressive power of NPDA, both are different. So based on this, here also, if you observe, the expressive power of this Turing machine is more than expressive power of this Turing machine, halting Turing machine. So expressive power in the sense number of languages accepted. If you see, this is what is this halting Turing machine? Halting Turing machine is nothing but it is a Turing machine. It takes the input, halt for every input by saying, by halting in, sometimes it will halt in the final state, sometimes it will halt in the non-final state. It reads the input and it halts in the final state for valid strings of the language, halts in the non-final. See, like our finite automata, take finite automata, give whatever may be the string, whether it may be 1A, 1B, 2A, 2B, whatever it may be, if it is a valid string of your language, like we constructed finite automata for A power n, B power n language, A power n, B power m, assume for this. FA we constructed. What this FA will behave? For all these strings, it will halt in the final. If I give any string outside of this, it will halt in the non-final. Definitely halting is there. So for valid strings of this language, halting is there. Invalid strings of this, halting is there. That guarantee will be there in the finite automata. Same nature in the push down automata. Even in the push down automata also, if I construct PDF for any language, for valid strings, it will halt. Invalid strings, it will not halt. But here, the Turing machine, so halting Turing machine will show the same behavior. For valid string, it will halt, say yes. Construction part is similar, whatever we constructed in the last class. Today we are not observing in the construction, we are observing the property of the Turing machine. So for invalid strings, for any language, if you construct a halting Turing machine, for that language strings, it will halt in the final state. The strings belongs to that language, it will halt in the non-final. Halt means stop. So that haltage will be always there for valid strings and invalid string in case of halting Turing machine. But that is not the case here. If you observe this Turing machine, this is a general Turing machine. For some strings, for any language, if I constructed this machine, for any language, the strings of that language, the machine halts. For any language, if you constructed this Turing machine, for the strings belongs to that language, it will halt in the final state. Whenever I say this is nothing but final state. Halt in the final state says yes, the string is accepted. But the strings not belongs to this language, for which two possibilities are there. It may say no, rejected. Yes, no means accepted, rejected. It may say no, or it may go to loop. There are two possibilities. So like this Turing machine will behave. So based on its behavior, the language also will be classified into two categories. The language of this category called as recursive languages. The language of this category is called as recursive enumerable language. So this is the classification. And what way we classified the language into the language of Turing machine into two categories, recursive and recursive enumerable language. Means for any language, if we able to construct halting Turing machine for all inputs, whether it may be valid input of the language or whether it may be invalid input of the language, if you are in a position to construct halting Turing machine always, then that language comes under recursive language. Recursive enumerable language means for any language, if you construct a Turing machine, then that Turing machine halts for valid strings of the language. The Turing machine halts for strings belongs to that language. Whenever the string not belongs to the language comes, the Turing machine will show two different behaviors. That is, sometimes may halt in non-final by rejecting. The no means reject here. Here also no means reject. Rejecting, or it will fall into loop. This is infinite loop. It's not normal loop. It fall into infinite loop. So these type of situations also there in the Turing machine. So now the thing is, whenever a language is recursive, this becomes under our decidability. Then we'll call that is decidable. It is decidable. Whenever a language is recursive enumerable, it is not a decidable. So here the decidability, undecidability, not decidability, those things are going to come here. So if you want to say decidable, that's why recursive language also called as Turing decidable languages. Turing decidable languages. Recursive enumerable languages are not decidable, not comes under decidability. So this is, so today I told you this is our undecidability concept. Here we are concluding about decidable, undecidable things. What does that mean? Is it don't have any relation with Turing machine? No, no, definitely it is a concept of Turing machine based on this. Recursive languages, halting Turing machine, decidability, all together are same. So like this we have. Okay, let us study the definition of this one clearly here. First, recursive enumerable languages. Let us study the definition of recursive enumerable languages or type 0 languages. Read it once. Recursive means recursive enumerable languages are also called as type 0 languages. Are generated by type 0 grammars. Okay, anyhow, corresponding grammars also exist here. We have studied unrestricted grammars. Those are the grammars for our recursive enumerable things. Right. So recursive enumerable languages or type 0 languages are generated by type 0 grammars. So this is our main definition. What is this definition? Recursive enumerable language can be recursive enumerable language can be accepted or recognized by Turing machine, which means it will enter into final state. See this, REL can be accepted by a Turing machine. This Turing machine is not halting Turing machine. Whenever I said a default Turing machine, the Turing machine meaning is may or may not halting machine it is. Whenever we say Turing machine, it is may or may not halting machine. So recursive enumerable language can be accepted or recognized by Turing machine, which means it will enter into final state. It will enter into final state for the strings of the language. It will enter into final state for the strings of the language and may or may not enter into rejecting state for the strings which are not part of the language. If the strings not belongs to the language, for which it may enter into rejecting state or may not enter into rejecting state. May or may not enter. What does it mean, may not enter? The meaning of may not enter is enter into loop, infinite loop. It is entering into infinite loop. That is what the meaning of this one. Right? So recursive enumerable language can be accepted or recognized by Turing machine, which means it will enter into final state definitely for the strings of the language. For the strings belongs to the language, definitely enter into the final state. Strings not belongs to the language, then it will may enter into non-final state. Rejecting state means non-final state, or may not enter into non-final state, that is entering into the loop. That possibility will be there. It means Turing machine can loop forever for the strings which are not part of the language. Can loop forever. Turing machine can loop forever, not part of the language. REL language are also called as Turing recognizable languages. So the name of this language is also called as Turing recognizable languages. So this is what the meaning of this one. If I construct a Turing machine for any language, if we construct a Turing machine, for the valid string of this, it will halt, say yes. For invalid strings, it may say no or may loop forever. This is the Turing machine behavior. So this type of behavior will be there for the normal Turing machine. Right. Now let us go and see what is a recursive language? What is a recursive language? Recursive language means the language for which I am once again asking you guys, please tell me, is it my audio clear? Video clear? If you are facing any problem, please inform me. Right. A recursive language can be decided by a Turing machine, which means it will enter into final state for the strings of the language. And entering into rejecting state for the strings which are not part of the language. That's all. Loop possibility not there here. If loop possibility is not there, that is comes under clearly recursive language. So the recursive language Turing machine is, let me write here only. If you, for any language, if you construct for valid strings, it will enter into the final state, says yes, string is accepted. For invalid string, it will enter into non-final state, says no, string is rejected. So for valid strings, Turing machine says yes. By entering into final state, yes, accepted. For invalid strings, Turing machine says no. By entering into non-final state, says rejected. Right. So this is the language. This is a recursive because we can construct a Turing machine which will move to final state if the string is of the form a power n, b power n, c power n. For a power n, b power n, c power n, it will move to the final state, else move to the non-final state. That's all. Either final state it will halt or non-final state it will halt. There is no possibility of falling into infinite loop. That situation will not arise in case of this one. So the Turing machine will always halt. This is our main concept of recursives. Recursive language. So in this case, recursive language also called as Turing decidable languages. That is the thing. So recursive languages are nothing but Turing decidable languages. Recursive language also called as Turing decidable languages. Right. So the relation between recursive and recursive enumerable, if you see, again we have got two class of language, no? So let us study the relation between these two. So we have a relation for this in this way. So these are called as recursive languages. These are called as recursive enumerable languages. Recursive languages, recursive enumerable languages. Here our general Turing machine, let me say the halting Turing machine. Here is the normal Turing machine. This is our decidable. And we have one more class of language here called as non-RELs. This is the relation between these three languages: recursive, recursive enumerable, non-RELs. So if you observe in our Chomsky hierarchy, this is the Chomsky hierarchy, no? Here we have recursive language Turing machine. Again it will be further classified into, so we can construct a something here called as recursive languages, halting Turing machine for this, and here we have non-RELs as well, non-RELs. This is the position of these languages in the Chomsky hierarchy. Right. Then what is the important thing here is, So this is based on the classification of our machines. Based on the clarification of this one, halting and non-halting behaviors. If it is a halting one, the corresponding language is called as recursive. That is called as decidable. If it is may or may not halt for some inputs, the Turing machine's languages are called as recursive enumerable languages. And these recursive enumerable languages, once the language is recursive enumerable, it is not decidable. It can be undecidable, it can be semi-decidable. We have semi-decidability. Generally, semi-decidable language falls under this category. Right. So this is what the classification of these two languages. What is recursive? What is recursive enumerable? Recursive is very simple. For any language, if you construct a Turing machine, that will always halt. Recursive enumerable is for which there exists a Turing machine which may or may not halt. That's all. So recursive language is also called as decidables. Turing decidable language. Recursive enumerable also called as Turing recognizable but not decidable. So this is about recursive enumerable and recursive language. What is important here is in recursive enumerable after this, closure properties. So the detection is like this, based on you are able to get what is that. Whenever we are studying about languages, we are studying two things. One is detection, one is closure property. So every year, most of the times we will get questions from closure property. Observe last year paper. The last year paper also we have a question from closure property. The closure property of not one, closure property of all the class of languages, from where we have to. So what you do is study closure properties of next in the recursive enumerable. What you need to study is first detection. Halting behavior is the recursive. You may or may not halting behavior is there, not recursive enumerable. And we have may or may not halting is recursive enumerable. Sometimes Turing machine also not possible. No Turing machine. See here. Here no Turing machine exists. Turing machine also not possible here. There are such type of things. There we have this one. So this is clearly undecidable. This is decidable. This is our semi-decidable. This is the region. So here main thing is closure properties. So once you study the, if you make chart like this, you study all the closure properties. So union operation, intersection operation, complement operation, concatenation operation. How we are studying generally, whenever we are studying regular all these possibilities in regular. So regular language, it is closed. Intersection is closed for regular. Union is closed for regular. Complement is closed for regular. Concatenation for regular language almost all closed. All are closed. Like this. Then let us go for the DCFLs. So DCFLs, this is the case. Whenever we study DCFL separately, whatever the result is there, you write here. CFLs, intersection not closed, complement not closed, remaining closed. Seems. CSL recursive enumerable. Like this, you make a chart. See, these are some of the things I am preparing here. So board will not support more than this. There are so many other operations we can include here. Substitution, homomorphism, inverse homomorphism, reversal. You can find difference operation. That is also you can include. Complement is included. Like this, we have so many other operations. We can include subset operation. Like this, you study all the operations language by language. You make a chart like this. Prepare one chart. Based on this, we are getting beautiful questions every time in the GATE paper. Now let us see how this table will be used. And proofs of this we'll study in whenever we are studying regular topic, how it is closed, where it is not closed, what is the reason. Those things we'll study while in the topic study of the topic time. Then at the end of the class, you prepare a chart like this. Now my aim is not preparing this chart. In this class, you can make a table like this. So how to make this table is, that is the overall theory of computation class. My aim is how to utilize this chart to solve gate papers, questions of gate exam. There are so many questions from this. So in our whenever we are preparing for gate, at the end of this, two tables we have to prepare. One is this closure properties of all the language families for all the languages: regular, DCFL, CFL, CSL, recursive, enumerable, REL. Closure property. One is decidability and undecidability table, decision property table. These two tables we need to by heart. You need to remember. I'm not saying by heart. We'll get the logical things of this. How to get these things we'll prove while studying the particular topic. But remembering of this table is important. Now we'll see how we'll get the questions from this. This is one of the direct question. Context free language R. So this question came one time in paper. Now go for the context free languages. CFLs, context free languages are closed under union or not. He is saying closed, whether it is true or false. Union case closed. So it is closed. Let us write here. Next, what is next one? Complementation. Complement. No. Then intersection. No. Like this table is not given at the time of gate examination. They will not provide you table. You need to remember it. Now you can see the previous gate questions directly from table. But by using the table, how to solve the question, that application I'll show you now. Closed under clean closure. So clean closure also closed. So complement and intersection are not closed. Closed under clean closure. Union and clean closure are closed. If the question is context free languages are closed for, if the question is this, A and D are the answers. So closed under union, closed under clean closure. A and D can be the answers. If it is like this. If the question is not closed, B and C, MSQs. The questions, MSQ questions can be asked like this. This is one of the way. We can see some more questions. This is one more question. This is one more question directly from gate paper. You can MSQ you can say. L1, L2 are context free languages. See how this question is. L1, L2 are context free languages. R is regular. One of the following not necessarily context free. Not necessarily context free. What is the first one here? Concatenation. L1, L2 are two context free. What is its concatenation? You should know first. For that, you should know table. So let us go to the table. Concatenation, CFL, yes, means closed. If it is closed, what happened? Closed means the result of that falls under same language. If these two are CFL, its result also falls under CFL. That is the beauty of the table. I feel this is a 2-mark question. So like this. That is CFL, not necessarily a context free. So if these two are CFL, that is also CFL we are getting. That is not the way. With regular, intersection with regular. CFL intersection with R is a regular, no? CFL intersection regular is CFL. We want not necessarily CFL. We are getting CFL in these two cases. B and C are CFL. What about union? L1 is CFL, L2 is CFL. Check for the union of CFLs. Union operation in CFLs. That is S. That means what? So if I union two context-free languages, the result will be CFL. So if I union two CFLs, two context-free language, the result will be context-free language only. So still in these three cases, I'm getting CFL. But my answer is not necessarily context-free I want. So what is the intersection here? Closed or not closed? Look at this. Intersection. No. No means the coming result, no guarantee of CFL. Not necessarily CFL. So we may get CFL, may not get CFL here, no guarantee. So this is not necessarily a CFL. So our required answer will be this one. How I did this? If I know union is closed or not, from where I know? From the table. Similarly, concatenation, whether it is closed or not, how do I know? From the table. That is the use of the table. So if we have the table information, just remembering is not required. Whether it is closed or not closed, like this they don't ask. They will make some operation like this. They'll apply, they'll take two languages, three languages. They'll apply intersection, closed or not. They'll apply union, closed or not, like this. Even if given like this, with the help of the information of the table also based on our previous knowledge, we prepared it. So based on that knowledge, if questions given in this way, we can easily solve. Majority of questions are there, including last before year, almost all in every paper these type of questions are there. Right. This is one more question. R1, R2 are regular. Regular set means language defined over the alphabet. Then R1, R2 regular, then is performing on intersection. What is the intersection for regular? Check the table. Intersection for regular. Yes, regular may everything is closed. So based on this should be regular. Intersection should be regular because R1 and R2 are regular. R1 union R2, this is also regular because union also closed. What is R1 star? Clean closure. This is also regular. Then what is this? Sigma star minus R1, this is nothing but complement. What is the complement as per the table? Everything is closed, so complement is closed. So what is the result of this? Definitely regular. So this is the true. So what he is asking is, he is giving wrong answers. This is wrong. If this is the case, then this is wrong, this is wrong, this is wrong. So complement is regular. This is the correct statement he framed here. Like this. So if we know the meaning of this operation, if we know whether intersection is closed or not closed, then only we can able to answer this. Whether it is regular or not regular, if we have that information. Where do I get that information? That information is already there in the table format. So the table is the main important thing for us. So there are so many questions of this kind. This is one of the very beautiful question. This is one of my favorite question actually. L1 is this one. L2 is this one. L1 is A power n, B power n. Here he has given two statements. L1 concatenation L2 is regular. What he is saying is L1 concatenation L2 is regular. That is the first statement. L1 concatenation L2 is regular. So regular language closed under concatenation or not? Look at the table, it is closed. So this is a regular language, we know. We can easily construct a DFA. This is also regular language, we know. We can easily construct a DFA. If we want the regular expression for this is A star, regular expression for this is B star. In order to avoid your confusion, I am constructing the regular expression as well. For any language, regular expression is there, that is regular. So that is A star regular, B star regular. So what is saying? So this is nothing but A star, B star. In the first statement, he is saying concatenation of these two regular. Yes, true. This is clearly a true. This is clearly true. Then L1 concatenation L2. L1 concatenation L2. What is L1 concatenation L2? L1 concatenation L2 is nothing but, see, this language A power n, B power n is clearly non-regular. Non-regular. Now generally where students confuse is, sir, this is A power n, this is a B power n. Its concatenation will get A power n, B power n only, no? Like this you may think. Its concatenation will get A star, B star. Because this is A star, this is B star. So concatenation of these two we will get A star, B star, but not A power n, B power n. There is a lot of difference in A star, B star and A power n, B power n. Both are completely different because this is equal number of A's and B's. If I take 2 A's here, definitely 2. But in this case, if I take 2 A's, here I can take 10, 20 B's, 100 B's, anything. So the concatenation of L1, L2 is nothing but A star, B star, which is not A power n, B power n. So what he is saying, which of the following is correct? He is saying this is also regular. So he is saying that L1, L2 is nothing but A power n, B power n. He is saying this is clearly false. How it is? The concatenation of these two will get A star, B star, not A power n, B power n. So which of the following is correct here? The correct is nothing but only one. Right. So with this, we can move to directly. There are so many questions of this kind. Undecidability. Undecidability. So that is about previous closure properties. Once closure properties are over, then next questions, high chance of getting questions. Most of the times we are getting questions from this topic is undecidability. Right. Undecidability is Turing machine concept. Based on Turing machine, we have concluded so many problems. There are so many problems for which we can write an algorithm, it becomes decidable. Algorithms not exist, undecidable. So in our formal languages, regular, DCFL, CFL, CSL, for this, what type of problems falls under decidable, what type of problems falls under not decidable. That is what this table is. This is also table, very, very important one after our formal language. Why I am showing this table directly is, these two tables will definitely give you 2 marks in the GATE exam. These two tables, formal language table, this decidability and undecidability table, these two tables definitely give you 2 marks, almost 2, sometimes if you are lucky 3, 4 marks also, maximum 3, I guess. If you are very lucky, then 4 marks as well. There are so many papers, observe in previous papers, direct questions from these tables. Now let me explain about these problems roughly. Then I'll move to our how to apply this for our given questions. Okay. Because the study of this takes a lot of time. For this lecture series, this is our last class. So I am directly telling you the application of this. So first one, W belongs to language. Does W belongs to language? This is called as membership problem. Membership problem. What is this membership problem is whether a given string is belongs to the given language or not, given string is belongs to the given automata or not, given grammar or not. I'll take one string, one automata. It is member or not. It is belongs to that or not. It is accepted by that or not. So this problem is decidable for regular, decidable for DCFL, decidable for CFL, CSL, recursive, undecidable for RELs. Here, this is the case where it is undecidable. In our classes, normal classes, this is just a normal series, so it's a very short lecture series. I am directly including the table. In normal classes, we'll prove this, how we are getting this, what is the reason behind this. So many things are there. But now, direct application of the table, how to use this by using just this table, how to score marks in the paper. That is what we are focusing in this class. Right. Next one is emptiness. This is called as emptiness problem. Is L equal to null or L equal to 5? This is called as emptiness problem. Now this is decidable for regular, decidable for DCFL, decidable for CFL, remaining cases undecidable. You don't worry about getting the reasons. Try to understand where it is decidable, where it is undecidable. Try to remember this table based on this. This is called as completeness problem. Completeness means either given language is complete language or not. Given grammar is complete language, complete grammar or not. Given automata accepts complete language or not. The complete language is nothing but sigma star. So given automata accepts a complete language. Given grammar generates a complete language. Given automata accepts a complete language. This total structure. So this is decidable in these two cases. Undecidable for remaining cases. Equality problem. Whether two automata, given two automata equal or not, two grammars equal or not. So equality problem. If I give two automata, they are equal or not. Two grammars, they are equal or not. Two languages, they are equal or not. The checking of these two, decidable or undecidable. This is, we can decide, we can write algorithm in these two cases. Hello sir, Venkat DS sir, welcome. So today our session is on undecidability. We are enjoying the undecidability table. Right. Then subset problem. This is called as subset problem. So these are the decidability and undecidabilities of subset. What is a subset? If I give two languages, L1, L2, whether first one is subset of second one or not. We have a subset operation in closure properties. Subset operation and subset problem both are different. So here this is subset problem. If I have two languages L1 and L2, one is subset of other or not. That's all. If one is subset of other or not, that checking, for which if you want to write algorithm, that is possible only for regular case. DCFL in all the remaining cases, that is undecidable. Right. So assume like this, we have a chart. We have this table. Let me show you one of the regularity. Last one, look at our regularity problem. This is also decidable in two cases, remaining undecidable. Anyhow, reasons we are not studying in this class. Let us see the application of this. Let us move to the gate questions. There are so many gate questions on this type. So this is one of the question here. Our aim is, in today's session, our aim is we need to how to solve the questions with the help of the table. Table is ready made, that is there with us. You need not to do any additional work for that. How to apply this for these problems? Now let us see. Which of the following is false? Halting problem of a Turing machine, decidable or undecidable? So whether by reading the input, whenever he has given Turing machine, look at this. In a paper, gate papers, whenever it is given Turing machine, the default Turing machine is may or may not halting one, we need to consider. REL's machine, recursive enumerable language machine, is the default machine because type 0 language, the default Turing machine language are RELs. So halting problem. Halting problem means the general Turing machine high possibility of falling into loop. So whenever Turing machine is said, that is the REL one, we will not conclude that one as a decidability. Our decidability is nothing but halting Turing machine. So this is clearly undecidable. This is nothing but true. The halting problem of Turing machine is by reading a string, whether Turing machine halts or not, we cannot conclude. It is difficult to conclude because once it is entering into the loop, whether it is halts or not halts, we cannot say, because after 1 crore steps it may halt. We cannot wait until that. So this is an undecidable problem. Ambiguity problem of context-free grammars. Context-free grammars ambiguity is also undecidable. We don't have any algorithm to check the ambiguity. So this is also undecidable. This is also true. Given two arbitrary context-free grammars, it is undecidable whether L of G1 equal to L of G2. What is L of G1, L of G2? Which problem it is? It is a problem of equivalence. So here context-free grammars given. Let us go to the table. Equivalence problem is this one. Context-free grammars means context-free languages. What is this? The context-free languages equivalence problem is undecidable problem. So based on this, clearly undecidable. He is saying it is undecidable. So it is also true. So regular grammars are given. G1 and G2 are regular grammars. Whether L of G1 equal to L of G2. Once again, equality problem of regular. So check whether the equivalence problem of regular is clearly decidable. So equivalence problem of regular is decidable, but in this question he is saying it is undecidable. It is undecidable. That's why the false one is this one. Our required answer is nothing but. So in this question, these two options are directly from. These two are directly from our table. This is halting problem is a common one, RELs. That is undecidable known thing. So ambiguity problem of context-free grammars. Anyhow, while studying, this is a famous problem in theory of computation. That is also undecidable. What we are going to conclude from this topic is, from these questions is, all the questions very easily solvable if you able to remember this. This is a ready-made one. If you have the knowledge of this, because while generating the table, we'll see the logics, how this is decidable, how this is undecidable, we'll see the logic. But at the end of preparation, you prepare a table, we need to remember this up to exam. So in the exam, we'll get the questions of this type. We can remember this, it will save your time to answer questions directly. See, this is one of the question. I think it is for 2 marks. Direct gate question. This is a gate question. So consider the following problems. L of G denotes the language generated by a grammar. Okay. 4 statement he has given. Which of the following is correct? We'll read the statement. We'll read this statement. For an unrestricted grammar G and string W, whether W belongs to L of G. What is this problem? Whether W belongs to L of G is membership problem. This is called as membership problem. So this is called as the membership problem. String belongs to the language or not, means string belongs to the grammar or not, string belongs to the machine or not. Membership of unrestricted means type 0. Let us check in the table. Membership of type 0, undecidable. So this is, let us write here, undecidable. Directly from table. So all these are gate questions. Just remember the table. 80% of the gate questions of decidability and undecidability depends on the table. Given a Turing machine M, whether L of M is regular. This is called as regularity problem. This is also there in the table. Regularity. So last one, is a regular language or not? Is L is regular language or not? Regularity of Turing machine. Given in the table, undecidable. So Turing machine is given, unrestricted grammar is given, RELs given. We have to check in the RELs table only. Third one, given 2 grammars G1, G2, whether L of G1 equal to L of G2. What is the name of this problem? This is equivalence problem. Equivalence problem. Equivalence problem of, he just mentioned about the grammar. He just mentioned about the grammar, not given anything related to whether it is context free or not. The default we have to see from RELs. So equality of this is undecidable. So 2 grammars given, equality of this is undecidable. By default case, RELs, REGs. Then NFA is given, PDA is given. Equivalence problem of this one will be deterministic PDA, DPDA. If you see the equivalence problem of DCFLs, decidable. So this is decidable. Which of the following statement is correct? So clearly 1, 2, 3 are undecidable. Like this we have so many questions. So once you are familiar with this table, if we are able to analyze things from the table, then solving the questions will be very easy. Like this, my advice is, by end of your concepts of theory of computation, you prepare 2 tables. One is a closure property table, one is decidability and undecidability table. With the help of these 2, we can solve the questions related to closure properties, decidability and decidability concepts. Okay. Okay, students. So this is about our total lecture series on theory of computation. So we started from finite automata topic. We studied all the concepts of finite automata, and then we moved to regular expression, then regular languages, grammars, push down automata, Turing machine. So actually this is whatever we covered here. I have taken only 15 lectures here. In general, in normal classes for complete coaching, GATE coaching for this subject, I used to take almost 70 hours, 70, 65 to 70 hours generally I take. So whatever is possible, I introduce some of the important concepts only here. So the total subject, mostly in the coming classes, I may introduce in the YouTube. By that time, it will be going in the GATE Wallah. Okay. I hope you enjoyed these sessions on lecture series on theory of computation. Soon I'll launch one more session on some other subject like compiler design or any other subject. Okay. Okay, guys. Thank you all. We'll see you in the coming classes. Bye bye.